Our solar system is a remarkable place. A place where a star, our sun, presides over a cosmic ballet of planets, moons, asteroids, and comets. But have you ever wondered how this intricate system came to be? How did our very own planet Earth form amidst this celestial dance? The story begins approximately 4.6 billion years ago. Imagine a time before our sun, before the Earth, before even the faintest glimmer of life. All that existed was a vast and cold cloud of gas and dust, adrift in the depths of space. This cloud, known as a nebula, was the birthplace of our solar system. This nebula was not unique. Such clouds are scattered throughout the universe, remnants of past stars that lived and died, seeding the cosmos with the ingredients for new generations of stars and planets. Our own solar system, our sun, our Earth, and even ourselves are all products of this cosmic cycle of stellar life and death. The nebula that birthed our solar system was a chaotic place. It was a swirling mass of hydrogen and helium, the most abundant elements in the universe, along with traces of heavier elements forged in the hearts of long-dead stars. These heavier elements, the carbon in our bodies, the oxygen we breathe, the silicon in our computers, were essential for the formation of planets like Earth and the emergence of life itself. Within this swirling cloud, gravity was the architect of creation. Gravity, the force that draws matter together, began to pull the gas and dust particles towards each other. As these particles collided, they clumped together, growing larger and larger over eons. This process of gravitational collapse was slow and gradual, but it was relentless. As the cloud contracted, it began to spin faster and faster, like a figure skater pulling in their arms. This increase in spin was a consequence of the conservation of angular momentum, a fundamental law of physics. As the cloud continued to collapse, it began to heat up. This heating was a result of the increasing density of the gas and dust. The particles were colliding more frequently and with greater energy, converting their kinetic energy into heat. At the center of the collapsing cloud, a dense and hot core began to form. This core, known as a protostar, was the embryonic stage of our sun. As more and more material fell onto the protostar, its temperature and pressure continued to rise. The protostar was not yet a true star. It was still shrouded in a thick cocoon of gas and dust, obscuring its light from the outside universe. But deep within its core, a transformation was about to occur, a transformation that would ignite the sun and bathe our solar system in light and warmth. The protostar at the heart of our nascent solar system continued to accrete material, its core becoming ever denser and hotter. Temperatures and pressures at the core soared to unimaginable levels, millions of degrees Celsius and billions of times the pressure at the Earth's surface. Under these extreme conditions, the hydrogen atoms in the core began to fuse together, forming helium and releasing an enormous amount of energy. This process, known as nuclear fusion, is the engine that powers all stars. With the ignition of nuclear fusion, the protostar was reborn as a star, our sun. A vast amount of energy radiated outward from the sun's core, pushing against the inward pull of gravity. A delicate balance was achieved, a state of hydrostatic equilibrium where the outward pressure from fusion balanced the inward pull of gravity. Our sun had reached maturity. While the sun was igniting at the center of the collapsing cloud, the remaining gas and dust continued to swirl around it. As the cloud spun, it flattened into a disk, much like a spinning ball of dough flattening into a pizza crust. This disk, known as a protoplanetary disk, is where the planets of our solar system would form. The protoplanetary disk was not a uniform structure. It was hotter and denser closer to the sun and cooler and less dense farther out. This temperature and density gradient would play a crucial role in determining the composition and characteristics of the planets that would form within it. Within the swirling protoplanetary disk, dust grains, tiny particles of rock, ice, and metal, began to collide and stick together. This process, known as accretion, is driven by electrostatic forces and the tendency of small particles to clump together in the presence of gravity. As these dust grains continued to accrete, they grew larger, forming pebbles, then boulders, and eventually planetesimals, bodies that were kilometers in size. These planetesimals were the building blocks of planets. The process of planet formation was a chaotic and violent one. Planetesimals collided with each other at high speeds, some shattering into pieces, others merging to form larger bodies. Over millions of years, the largest planetesimals in each region of the disk swept up most of the remaining material, growing into protoplanets, the precursors to the planets we know today. The early solar system was a chaotic and violent place. Planetesimals and protoplanets were constantly colliding with each other, their orbits intersecting in a cosmic billiards game. These collisions could be catastrophic, stripping planets of their atmospheres, tilting their axes, and even ejecting them from the solar system entirely. One such collision is thought to have formed our own moon. Early in its history, the proto-Earth collided with a Mars-sized object, ejecting a massive amount of debris into orbit. This debris eventually coalesced to form the Moon, our constant companion in space, about 500 million years after the formation of the solar system. The inner solar system experienced a period of intense bombardment known as the Late Heavy Bombardment. During this time, a large number of asteroids and comets from the outer solar system were flung inwards, colliding with the inner planets and their moons. The Late Heavy Bombardment had a profound impact on the early Earth. The impacts delivered vast amounts of water and organic molecules to our planet, potentially playing a role in the origin of life. However, the bombardment also sterilized the Earth's surface, delaying the emergence of life until after the bombardment subsided. Amidst the chaos of the early solar system, Earth emerged as a haven for life. Our planet's unique position in the habitable zone, the region around a star where temperatures are just right for liquid water to exist on a planet's surface, allowed for the formation of oceans, the cradle of life. The early Earth was a very different place than the planet we know today. Its atmosphere was toxic, its surface was bombarded by asteroids and comets, and its continents were still forming. Yet, despite these harsh conditions, life found a foothold, emerging in the oceans and eventually spreading to every corner of the globe. The formation of our solar system is not unique. Astronomers now know that planets are common around other stars, with billions of planets estimated to exist in our galaxy alone. Many of these planets are very different from the planets in our solar system, challenging our understanding of how planetary systems form and evolve. The search for other worlds is one of the most exciting frontiers in astronomy today. By studying exoplanets, planets orbiting other stars, we can learn more about the diversity of planets in the universe and the conditions that give rise to habitable worlds like our own. The story of our solar system's formation is a story of cosmic evolution, a story that spans billions of years and connects us to the vast universe beyond our planet. From a cloud of gas and dust, gravity sculpted a star and a system of planets, one of which, our Earth, became a cradle for life. As we continue to explore the cosmos, we gain a deeper appreciation for the rarity and preciousness of our own planet. Our solar system is a reminder of the interconnectedness of all things and the incredible power of nature to create complexity and beauty from simplicity. But before that future unfolds, our story continues with another chapter. Join us in the next episode of The Formation of Earth, as we journey from the solar system's dust to the creation of our own home among the stars.